G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or good evening. And I pray God is blessing you and your study, and I pray your pracs have gone well, because by this stage you should have done some pracs. Okay, this is lecture 11. This is part A of lecture 11. There's going to be at least 3 parts to lecture 11. This is the final set of lectures before week 12. Week 12 will be revision. So let's get into this. God bless you as we study together. Okay, so we're going to look at topologies, fine and coarse topologies, metric and cofinite topologies, subspaces and bases, and lecture 11b will continue on from bases. So lecture 11c. Okay, topological space. Now this is from lecture 10, just as a reminder in case you haven't seen lecture 10 for a while. Topological space is defined in terms of open sets. A topological space is a set of points combined with a collection of its subsets called open sets, so that's important, which satisfy the following axioms. The empty set is open, the entire set is open, the union of any number of sets is open, and the intersection of a finite number of sets of open sets is open. Okay, so that's just a reminder from lecture 10. Topologies. Here I've picked 4, which I think are relevant. Obviously, 2 of them are essential. The discrete or the fine topology, which is every possible subset in an open set, e.g. for AB, the open sets would be empty set A, B, and AB. So if that's just we're looking for that. An indiscrete or trivial coarse topology, the only sets are the empty set and the set itself. So if X was the set, then the open sets would be the empty set and X. And that was it. Okay, if it was AB, it would be AB and the empty set. That would be it. A metric topology, I thought these other two I thought were relevant. Metric topology because it's numeric, defined by a metric of a distance function on a set where open sets are defined as balls. And a cofinite topology. Open sets are the empty set and all subsets whose complements are finite. So I thought these 4 are relevant. There are a bunch of other topologies, but they go on and on where mathematicians have come up with ideas and say, oh, here's another way we can look at it. It's like, oh, that's great, congratulations, but we don't really need to look at every single topology. Just looking at fine and coarse topologies. Fine topologies have the maximum number of open sets. Coarse topologies have the minimum number of open sets. So it's pretty easy to delineate these two. For example, I'm giving a concrete example, a great way to remember mathematics. Given the set X equals 1, 2, 3, the fine topology of X is the empty set, 1 on its own, 2 on its own, 3 on its own, 1, 2, 1, 3, 2, 3, and 1, 2, 3. Now, be aware, these are open sets. So if this was a square bracket, it would just be 1. This is an open set of 1, which means it's going up to 1. So if you wanted to have a set separate to this, it would have to have an open bracket and be 1, where 1 is not included because 1 is already here. Okay, so these are open sets. A coarse topology of X is the empty set and the whole set itself. That's pretty easy. Now, what I did was I thought, hey, I know, I do a bit of manual work, which is good, and I use sandpaper. So this is fine sandpaper, and this is coarse sandpaper. And I thought, hey, it's great to give mathematics students concrete things to remember things, which you can do in your class with your students. So fine sandpaper has lots of small grains, lots and lots of things. Fine topology has lots and lots of things. Coarse sandpaper has very few big grains grinding off stuff. So coarse topology has very few things. In fact, it's only got 2. Okay, hopefully that's a helpful thing for you to help remember fine and coarse topologies. It may or may not be, but I was just trying to think of something a bit more concrete for you. Okay, so there's fine and coarse topologies. Metric topology, move the image down the bottom. A metric topology is defined by a metric distance of a function on a set where open sets are defined as balls. So for example, 1, and these will be very concrete and you'll be used to these. the absolute distance between two numbers on the real number line. For example, distance xy is x minus y absolute value. Pretty easy, you would have done that before. Example 2, distance between 2 points on a number plane. x1 minus y1 squared. There should be a plus in there, shouldn't there? Whoops. Plus y1 minus y2 squared. So, sorry about that. I have to put a plus into the notes. And again, we've referenced Pythagoras again. I think this course references Pythagoras a lot. Last one, cofinite topology. I've included this one because I thought, for me, this one is the most interesting. Cofinite topology, open sets are the empty set and all subsets whose complements are finite. So, example 1, let E be the set of all even numbers in R, which is open. Okay, because unlimited even numbers in the reals. Its complement, let's call it F, so I've just made up E and F. Let's call it F, is a set of odd numbers in reals, and that's also open. So therefore, when we look at E, so E is the one we're looking at, E is not cofinite. We don't care that E is infinite, that's irrelevant. For a cofinite topology, what we want is the other set to be finite. So the other set in this case is the odd numbers, it's not finite. So therefore, E is not cofinite. You can't say it's cofinite. Here's a second example. Let P be the set of all real numbers except for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is open. That's infinite. So that goes from minus infinity up to not including 0. And this goes to not including 10 up to infinity. So that is open. So that's P. And then its complement, let's call that Q, is a set 0, 1, 2, 3, 4, up to 10, which is finite. So now, if we look back at P, we can say P is cofinite because the other set, its complement, is cofinite. Is finite. Okay, so we can say P is cofinite because its complement is finite. I find this interesting mainly because I do a lot of thinking as a mathematician, which I'm sure you do as well. It's got an application to real-world problems in computer science, gaming, robotics, GPS, and molecular biology. So I'll tell you what I mean by that. Imagine you've got a big problem in computer science or in molecular biology or dealing with GPS. You say, this is the whole problem. It's huge. It's like a worldwide problem for that, for the computer game or for the human body. You go, I can't solve the whole lot. Okay, what bit can I sign? Okay, well, what bit can I solve? If I split the whole thing into something that's infinite, which is sort of, I'll leave that as unsolvable, and then I've got a cofinite section, now I can solve it. And you can actually do a lot of maths working with this type of topology to solve problems. So these are real world situations in which this sort of topology is used. So I find that interesting. You might not, but I find it quite fascinating that we're using a specific type of mathematics to solve or split up things. Okay, subspaces. Let V be a vector space and W be a subset of V. W is a subspace if and only if it satisfies the following three conditions. It contains the zero vector, it's closed under addition, and it's closed under scalar multiplication. So you want those three things. Now you may have done that previously in first year or second year maths. We're doing it again because it's part of like the whole lot of the mathematics course. So if you have never seen this before, now you have. But hopefully you've seen that in a little bit in first year and then a little bit in second year. For example, here we go. Any plane that passes through the origin, 0, 0, 0, is a subspace in R3. Example 2, any matrix which can be solved as AX equals 0, for example, 1, 1, 2, 2, or 1 minus 1, 2 minus 2, which in this case I'm helping you out here by simplifying it. So these simplify to 1 plus 1 or x1 plus x2 equals 0 or x1 minus x2 equals 0. And obviously if you're doing that's x and that's y, these all result in the null space. Okay, so if you can resolve it to that, then you get the null space. Okay, they're just the examples. And here's a proof. And this is more likely to be the sort of question you get in an assessment. Prove that V equals x1, y1, x1, x2, x3, which are elements of R3, where x1 minus 2x2 is 0. So this is the condition, and it's a really simple condition. I'm going to prove that this is a subspace of R3. So what do we want to do? Oh, just a note here. Being a subset has no additional conditions, right? We really don't, that has nothing to, if you've got 2, 3 is a subset of 1, 2, 3, you don't have to do anything to prove that 2, 3 is a subset of 1, 2, 3, other than saying those numbers are in that set. Ta-da, done. Pretty easy. But being a subspace has to satisfy those three conditions of 0, addition, and multiplication. Okay, so being a subset, no conditions other than, yep, those numbers are in there. Subspace, we have to satisfy the conditions. So we're going to prove that this is a subspace, and it's a very straightforward proof. This same proof can be applied to any question you get, obviously with different numbers and letters. Okay, so we're going to create two things in V. So we're going to let A equal A1, A2, A3, and B be B1, B2, B3. Then, because they are now in V, then this bit must be true, because we're saying this is V. Okay, so if this is A, then A1 minus 2A2 is 0, because that's the condition of V. And if for B, then B1 minus 2B2 is also 0. So these are now true, because we've said this is now in V, and this is now in V, and this is what we're using. And what we're going to do is use these to do 0 addition multiplication, which is pretty obvious. You probably already figured that out. So it contains a 0 vector. We're not going to use both of them because that wastes time. We're just going to use one. So let's just use A. So if A equals A1 is 0, A2 is 0, A3 is 0, then here, let's apply the condition. 0 minus 2 times 0, we're taking that 0 and that 0 specifically because A1, A2 equals 0 is true. So V contains a 0 vector. Tick, we got the first one. Satisfies vector addition. So let's do the second one. So A plus B, so we're going to get A1 plus B1, A2 plus B2, A3 plus B3, and then we're going to apply this to the condition. So there's our condition again, x1 plus minus 2x2. So this would be x1, so A1 plus B1 minus 2 times x2, which is A2 plus B2. So there we want this to be 0. So we can split that up pretty easily just by distributing backwards. So A1 minus 2A2 plus B1 minus 2B2. And we know already that these are the conditions there. That's 0 plus 0, so that equals 0. So that's true. We've got satisfying vector addition. One more, we need multiplication. So for this one, because once you start doing it, you go AB, A1, B1, A2, B2, A3, B3. A really good way to do that when you've got multiplication, say, okay, these things are multiplied together. I'm going to say that is now going to equal a new value, C1. And this is now going to equal C2. This is going to now equal C3. Then we can say A1, B1, which is up here, minus 2 A2, B2, which is here, equals C1 minus 2C2. And now we can say that that applies here. That's the same. So that's the same as the original value where you've got x1 minus x2, we've got that equals 0. Therefore, it's true. My image is about to be in the way of the conclusion. Therefore, V is a subspace of R cubed. Okay, or R3. Okay, so we're just showing each of those three things are true. Therefore, we can say it's a subspace. And I think this is a little neat trick you can use to say, okay, I've got three elements. I'm going to combine them together to call them a new element or a new value because they are just, in this instance, they're just constants, or there'll be some value. Okay, hope that makes sense. A basis or a basis, it really doesn't matter about your spelling here because they're used interchangeably in maths. A basis is defined as a set of elements from which other elements can be generated. Again, you've probably seen this in first year and second year. Examples. A basis for a topology, you may not have seen it for a topology, but you've probably seen a basis. A basis for a topology, which is a collection of open sets from which all other open sets can be formed by union. and a vector space basis, and you've probably seen this one, which is a set of linearly independent vectors that can form any other vector in the space. Now, you've almost certainly seen this word linearly independent in first year and second year, and if we want two vectors that are linearly independent, here's a reminder. Linear independence is shown by the determinant not equal to 0. If the determinant equals 0, you're going to get linear dependence. Okay, so there's your reminder. Thanks, Dr. Everett. Really appreciate those reminders. Okay, terminology for a basis or basis. R2 or R3 with the number up the top is how to express real vectors in 2 or 3 dimensions respectively, etc. So R4, R5, the number goes up the top. Basis for vectors. The standard basis for vectors in R2 is 1, 0, 0, 1. Since any vector in R2 can be written as A multiplied by 1, 0 plus B multiplied by 0, 1, where A and B are reals. Okay, so note that dim R2 is 2. The dimension equals 2. The dimension of R2 is 2, which means there must be 2 vectors. Here's one of them, here's another one. There must be 2 vectors to be a valid basis of the vector space. E.g., you must be able to create, for example, I'm making this up, you must be able to create 3 minus 2. Right? You must be able to create that using this basis, which we can. We can go, if A is 3 and B is minus 2, bingo, I can create 3 minus 2. And I've just used this as an example of a positive and negative with numbers that aren't 1, so that you've got it in your head of, okay, I've got to be able to create another vector, and this is the only way I can do it, by using something like this. For example, is 1, 0, this vector, a valid expression for a basis of vectors, of vectors in R2? Answer, no, since it's only got dimension 1. So here, look at this. We'll put an A in front. I can get A, if A is 3, I can get, that's a 3, 0. Yep, I can tick off 3. But there's no way I can turn this 0 into minus 2. I need another vector. I need dim to be 2, the dimension to be 2. I need another one down the bottom. Now here where I've got 1 and 0 and 0, 1, that's great. That's the perfect situation. But you could also equally say, well, I can get another set of vectors where I've got 1, 0 and 0, 2 or 0, 3, because then I can just change the value of B. So I don't necessarily need 1, 0 and 0, 1, although that's a lot easier to deal with. I just need to be able to make sure I can get to another, vector. Okay, and I'm using this. Hopefully that sticks in your mind. You think, right, I've got to be able to get to there. Can I get to there with this? No, no chance. Especially since the dimension equals 1. If I'm asking, or the assessment asks for a reason, that's going to be the main reason you can't do it. The other reason would be it's linearly dependent. Okay, so that's vectors. Let's look at matrices for a basis. So M2 by 2 or M3 by 3 is how you would express a 2 by 2 or 3 by 3 matrix, respectively. So you've got the numbers here down the bottom. So when you're using M, numbers down the bottom. When you're using a vector, numbers up the top. So basis for matrices. The standard basis for a matrix in M2 by 2 is 1 up there, a 1 up there, a 1 down there, and a 1 there. Again, you can put these in any order, it doesn't really matter, but that would be a basis for a matrix in 2 by 2. Any matrix 2 by 2 can be written as A times the first one, plus B times the second one, plus C times the third one, plus D times the fourth one, where A, B, C, D are reals. Okay. Note that dim M for a matrix 2 by 2 is 4. Okay, we need 4 matrices for this to work out. There must be 4 vectors or 4 matrices. Actually, I should say there's 4 matrices to be a valid basis of the vector. Well, that should be the matrices space. Vector space. It's a basis for the matrix. I should have used matrices there, not vector space. You must be able to create, for example, and again, I've made up another one. Again, you've got to be able to create 3 minus 2, 4, 1. And you can pick any other random collection for you to make up, but you've got to be able to create this. If you can't create this by using different values, then it's not going to work. Example, is the identity matrix a valid expression for a basis of matrices in M2 by 2? Answer no, since it's only got a dim 1. Now you might be able to think, well, I could create another vector where I've got, let's say, 1, 0, and I've got the other one as 0, like if you had B and you just put a 1 there, so that covers all 4 spots. The problem is, once you put in A, you're going to change both of these to always be the same. Okay, so if I had an A there plus B is the other one, so 1, 0, the opposite of identity with the diagonal, then these two would always end up being the same. If I made a 3, and there's a 1 there, I'm going to get 3 and 3. I can't get that 1. Or if I just say, if I put A as a 1, I can make that a 1, but I can't turn that magically into a 3 because it's going to be a 1. Okay, so that's a good way to remember it, is you've got to be able to create some random collection of the matrices. Okay, that's all I've got for part A. I've made up some questions. I've made up 4 questions for you to do as practice. So there's 1, 2, 3, and there's 4. And I will see you in part B. Stay safe. God bless you. Go and have a hot chocolate, coffee, or maybe a glass of water. Okay, bless you. Bye.